way? Okay.
The theory is that those of us who are standing up here, then they can sort of hear us talking, and the people back there who can't hear us hear the stereo. Yeah. So that's probably not how it actually works, but that's our theory. Okay, so hi everybody. I want to start by welcoming you and thank you so much for coming out. This is the Silicon Valley Deep Learning Group. So if you are looking for some other group, this is the last opportunity to get off the airplane. This is I don't know. This is maybe our 15th or 16th event, something on that scale, maybe even more. We've been running the group for about a year and a half. This is actually the smallest event we've ever had. So we have very limited seating for this event, but a really, really nice venue. And I'll talk more about our awesome sponsors in a moment. But we have had every event has been completely booked for the last several events, quite a few in fact. The total number of members in the group has grown really substantially. So there's now, I don't know, where Sophia's around here somewhere. So I think we just passed 3,600 members. So for those of you who are coming and viewing here and actually coming and taking part in the deep learning group, that's fantastic. But there's also a tremendous audience growing of people who are able to enjoy these videos online and learn from them and learn from our speakers and get to know our sponsors and actually get to know all of you too as you ask questions and introduce yourself, stating your name and where you're from later on during the Q&A. So I'd actually like to introduce right now Zach Vogue, who is one of the founders and partners in DCVC, which is he will speak more about, but is our sponsor for our facility tonight, and who also provided us this wonderful food and drinks. But I will let Zach tell you a little more about his VC.
Thanks, Adrian. Hey guys, Zach Vogue of Data Collective. We're really excited to be hosting this event. It's an area that's near and dear to our heart. And a little bit about Data Collective. We're on our 6th fund. We've been investing, we're an early stage deep tech investor, and we've been doing this for the better part of 8 years, i.e. since before it was cool. And I was actually psyched. I'm psyched to hear Steven talking. I actually was psyched to see that he worked at Perceptio before Lambda, doing facial recognition software, which is one of my favorite examples that I tell to our investors that, 8 years ago, facial recognition was the creme de la creme hardest ML problem that everyone was trying to crack, and now it's on all of our phones, which is exactly what those guys were doing. Anyway, so I'll turn this back to Adrian to give a more complete intro for Steven, and thank you guys for making it out. Good to see everyone.
Okay, so I won't take much more of your time. So I'm going to introduce Steven Balaban from Lambda Labs. He's the CEO and one of the founders of Lambda Labs. And he's going to talk to us tonight about creative applications of deep learning, but I think he's going to tell us a little more about what Lambda Labs is doing in that space and beyond. We have a small display here, so Steven's going to be using a little bit of the display and a little bit just talking and maybe some interpretive dance or whatever if it seems that the video is too far away for you to see. So I'm going to pass the metaphorical talking stick, if not the physical mic, to Steven, and he'll take it from here. So let's all give him a big welcome.
Hi everybody, and thank you so much for coming today and seeing this. It will be a relatively visual talk, so feel free to take a look at the screen, and I'll maybe be doing some zooming in to make sure that everyone can see it. Oh, I'm so sorry for you. Can you see it? No, the screen right here. Yes. Okay. Good. Okay. I thought you were a little bit too far forward. Okay. So. All right, so the talk is creative applications of deep learning. It will mostly be about images, but it will also be about audio a little bit too. So let me get started. All right, so in the past, creativity used to be something that we would associate with the artist and the creative, and I think that maybe 5 years ago or 10 years ago, if you asked people, well, what was the last profession that will be automated? What was the last profession that will be kind of consumed by machine learning? And people would say, oh, well, either a psychiatrist or a artist. It turns out that I think that machine learning is really good at art, it turns out. So this is an example of a result of combining this photograph with this painting and saying, well, why don't you repaint that photograph for me? And so I think that artists should be sweating a lot and especially technical artistic skill, right? I mean, obviously there's the high-level creative input, but especially from a technical perspective, I would be worried if I was an artist. So a little bit about me, you guys already know. I'm the co-founder and CEO of Lambda Labs. I used to work at a company called Perceptio. We were running face recognition neural networks locally on phones' GPUs, and you'll see a nice demonstration of that today. That company ended up being acquired by Apple, and some of the tech is running on your phone. So I'm going to go into a little bit about. I think the point of this talk today, given that you guys are all deep learning practitioners and machine learning practitioners, I want to kind of give you some of the history and thought processes that led to the current breakthroughs in creative applications for deep learning. Because at the end of the day, the people who are publishing these papers are, in fact, no smarter than any of you in the room. It's just that they've been following the field for a long time, and the current state of the art is really just a sum of a few small steps along the way. And so I'm going to try and walk you through those small steps and kind of give you guys the kind of intuition that I've ended up building up over the years. I should say I and everyone else in the field. So probably the biggest start here is probably visualizing learned filters. So let's start with that. I would say that's the origin of a lot of these creative applications. The picture that's up here right now is first layer filters for a stacked denoising autoencoder that's been trained on the labeled faces in the wild data set. That's the data set that's like pretty much the, as of a few years ago, the de facto face recognition data set. And you can see, these are the filters that were learned on that. And so this is a little bit of an outline of the talk. I'll go back to this a few times. So, one of the earlier papers on filter visualization and optimization was this MNIST. It was a paper called "Why is Pre-Training Needed for Deep Learning?" And it was by the guys at University of Montreal. And you can see in this column here, it's a little bit difficult. I'll try and zoom in. Give me one second here. These are filters that are learned on MNIST. So this is a handwritten digit recognition data set. And you can see here there's a few different types of stroke recognizers at the lower levels. At the higher levels, there's maybe number part recognizers. And at the very highest level, there is kind of full number recognizers. Okay, and so these are the filters that have been learned. And these were calculated by saying, all right, choose one of those filters and start with the random input and maximize the activation of that filter. And so you start with random noise and you converge to this kind of stroke detector, which is then composed into a number detector. All right, so moving on to Commnets. So Zeller and Fergus, there's a 2010 paper as well as a 2014 paper for visualizing convolutional neural network filters. You can see here on the left-hand side, basically with their paper, they start with an image and then they run it in the forward pass and they project back to the original input image kind of the regions of that image that most activated that filter. And then so on the left you see those regions, and then on the right you see the image that caused that. And this is from the 2010 Matt Zeller paper, and if you're familiar with a little bit of the history of computer vision, you'll know David Marr's Vision book and his theory of basically the Primal Sketch, where there's a Primal Sketch, a 2.5D sketch, and then a 3D model. The Primal Sketch is basically a sketch composed of these we'll call, like kind of atomic tokens of vision. And it's kind of interesting to compare A, which is the tokens from David Marr's book Vision, and B, which is convolutional neural network filters that are from this Zeller 2010 paper. It's kind of striking, actually, to be honest. And it's very actually intellectually satisfying, I'd say, to say that there's some confirmation of David Marr's theory as well as kind of the Yoshua Bengio's manifold learning theory, where you have a kind of hierarchy of starting with low-level features, edge detectors, circle detectors, building up into these kind of more advanced, more complex, more rich features. In addition to that, you may be familiar with Hubel and Wiesel's paper, let's say Hubel and Wiesel's paper, they actually won the Nobel Prize for this research. They implanted electrodes into a cat's brain and they found out when they were showing it little tokens, it turned out that the edge of the slide was activating and causing these crackling pops in the electrode in the cat brain. And it turned out that edge detector was what was actually firing and causing the cat's visual cortex to fire. And it was just a kind of a rising edge stimulus. And so this is actually kind of funny. This is the PETA-approved version of this experiment diagram. Okay, this is the slightly more realistic, but still, PC will say version of this. The cat's kind of relaxing. And then this is the reality of it, which is the cat's kind of like screwed into this vice. Either way, it's Nobel Prize winning research, and so that's the reality of it. Either way, it's quite satisfying to see that some of this theory has, and more importantly, that our Commnets are learning in a kind of similar fashion to neural systems. Okay, so moving on from filter visualization, one of the really important aspects of visualizing these filters, especially with an optimization process, is introducing what's called a natural image prior. So if you do naive gradient descent on the data layer, on the data layer, you kind of get these very high frequency results. There's a good Simonian, and I think it's Zisserman. It's from Zisserman's group anyways, 2013 paper where they did basically backprop to the data layer with an L2 regularizer, and it had a lot of high frequency noise in it. So there's been some research using TV normalization, a Gaussian image prior, and so basically what they're doing here is when they do their backprop step, you do the update, and before you actually set the new X value in your update, right? The update, the kind of typical update function being X, arrow, X plus your learning rate, the gradient of the loss function with respect to the input. You have some sort of regularizer. In this Yazinski, this is from Cornell, Jason Yazinski et al. Paper, they use a Gaussian filter basically before doing that gradient descent update, and that really smooths the image. And so a lot of the research has been involved in finding good natural image priors. And finding good natural image priors is actually really important, and you'll see why soon. So this is with a Gaussian image prior, and it's really simple. It's just doing a Gaussian blur, before doing the update. It's very, very basic. The folks at Google, Chris Olah and a few others at Google have come up with an even better natural image prior, which is neighboring pixels are correlated. They accomplish this by essentially using octaves in the optimization. So you'll do it at you'll take the image, you'll, let's say, downsample to 1/8 the size. Okay, you'll do the optimization, you'll upsample that to 1/4 size. All right, you'll do the optimization, upsample that to 1/2 size, and so on and so forth. The effect there is when you initialize the optimization with that smaller thing, you basically enforce that neighboring pixels are correlated because they're basically forced to be initialized at the same point. If you think about it, right, it's like if you have a picture of me here and you downsample that and you upsample it, this entire region will be the same color as my shirt, and so it will force the Lambda logo to be the same even though it's black. Okay, and so those visualizations you can see are actually much better than these ones. So if we zoom in, we'll go to like layer. I think that layer 5 would be pretty equivalent. So you can see that these visualizations are not really not quite as clear. So for example, okay, I'll look at this one. I actually don't know what class that one on the right is, but maybe it looks kind of like a peacock, right? It looks a little bit like a peacock recognition system or a recognizer. And but if you look over here, these definitely look a lot more like those objects that we're trying to recognize. Very much like a banana, very much like a starfish, very much like a parachute or a screw. And so it turns out that that octaves provide a much better natural image prior. So this was probably this is the first image that was published publicly for Deep Dream, as you guys kind of you've probably everyone here has seen Deep Dream, or who hasn't seen Deep Dream? Anyone? Okay, one person. Okay, so but what Deep Dream does, it uses that same natural image prior, but instead of basically trying to optimize for the activation of one of the classes, right? These are classes, by the way, that are drawn from like ImageNet or something. And instead of trying to basically pin the class, it says, all right, well, I mean, on a technical side, it's doing what's called L2 maximization, where it's basically trying to, if the feature activation vector at that final layer is a point in n-dimensional space, let's say it's a 2000 class vector, that's like a 2000 dimensional space, it's a point in that space, you're trying to maximize the distance between that point and the origin, and that's what L2 maximization is. You know, that's like the Euclidean distance. What that means, basically, though, is that if it recognizes a dog-like object, or it recognizes, let's say, a slug-like object, it will push the input image closer towards that, and that happens in an iterative process. And so you'll say, okay, well, hey, the face of this is actually a squirrel, it turns out. The face of this squirrel looks a little bit like a dog, or like the tail of the squirrel looks a little bit like a dog face or something. In the same way that you and I look up into the clouds and kind of see objects. And so let's make it look a little bit more like a dog. So I'm going to paint maybe a dog face, a little bit like a dog face there, and then run it again and again and kind of go through this iterative process. And that's what Google Deep Dream did. And that was, I would say, Deep Dream really sparked really was the opening salvo in a lot of research in generative networks and a lot of research in creative applications of deep learning. I mean, basically, we've gone from visualizing filters and understanding what these networks are perceiving to actually creating new images. And that was a very exciting moment. And we ended up launching kind of a web service that did this called Dreamscope, which by now we've processed over 14 million images. We have like over 700,000 registered users on that. And we basically said, hey, there's some sort of interesting phenomenon here with how deep networks are changing how people are creative. And so these are a few more examples of Deep Dream images, maybe a little more artistic versions that were processed by Dreamscope. Okay. How many months later was it? June, July, August. Okay, August 20th or something, a member of this audience sends me an email, and he says, hey, Stephen, you got to check out this paper. And he's one of our investors, and it turns out to be this paper right here. And it's called Gattes. It's a paper from Germany, and basically this is going back to that original example. It's the foundation for this type of process. This is a custom. This is a really improved version of the algorithm. If you did the kind of naive version of this algorithm, it wouldn't look like that. But essentially, how that works. idea what size battery.
Continue with this guy.
Okay. Hello? All right. Testing. Can everyone hear me? Okay. So basically, this is basically what's called neural style transfer, and I'll walk you through this in after one sip. All right. So at the very high level, neural style transfer starts with the result image. It can either kind of be random noise, or it can be initialized with the content image. And so the content image in this case is of course the photograph, and this is what's called the style image. We'll refer to this as C and S, okay? And R being the result R. And it's purple because, if you merge red and blue, it's purple. Okay, so you start with some R, some result image, and you say, all right, minimize, it's a joint optimization essentially. You say minimize the distance in content space between the result image and the content image, and minimize jointly the distance in the style space of the result image and the style image. And those two functions, content loss and style loss, that you see up there are defined by neural networks. Okay. Got it? All right. Everyone loves lavalier mics. All right. Yes. Well, so R is the output. It also is the input. It also is the input. It is the output of. It's the final result that you return. But as you can also see, I should say this formula really is R equals a arg min essentially. Arg min. And arg min is always the complicated stuff, isn't it? Arg min of content loss, style loss. So R equals that, and it's an iterative process. So there's an update here basically. So there should be R arrow, some learning rate, content loss.
So but your web service allows people to provide as input C and then S.
Yeah. So Dreamscope, the web service, allows people to provide the content. We provide some style images. We also allow people to provide their own style images as well. And so that's neural style transfer. Yes, question?
Have you tried swapping C and S and see what you get as the R?
Swapping C and S. Oh, that's interesting. So I mean, if you were to swap C and S, essentially what you're saying is let's make the right-hand side look photographic. I'm actually going to show you a few examples of that going forward. So you've predicted kind of a later step that people have made. But in terms of, to answer your question, with this particular algorithm, it doesn't actually look very good. And I'll go into a few of the reasons for that. Question?
Do you also use the knowledge that we care more about things like eyes and certain facial features where you should probably take more, the result should probably be closer to the content in some areas and closer to the style in other areas?
Yes, and so the question, by the way, I'll just to rephrase the question is, shouldn't you take into account the, for example, the eyes in the content image and the eyes in the style image, and maybe say, okay, well, the eyes in the result should be closer to, let's say, the eyes in the style image, and basically figure out which parts of right. So eyes should be closer to the content image, and then maybe the background should be closer to the style image.
Actually, I was thinking of something similar, but rather than bias it towards the content, maybe just look at a correspondence between the eyes and
we're getting there. We're getting there. Okay, trust me. All right. Yeah. So that's exactly. There's a few papers published on that. And that I'll be going over. Okay. So essentially, you do this joint minimization, and you get a result image. It's this kind of painted version of it. Essentially, like I was saying, these two functions are defined by neural networks. One of them is essentially, let's say, VGG, which is like a very standard benchmark network that's been trained on ImageNet, and its feature activations correspond to like basically if you're to do a distance of those feature activations, that corresponds to a distance in content space. And then the main, I'd say, addition of this paper as to the literature is that if you take what's called a gram matrix, which is essentially the outer product of that feature activation with itself, which is kind of corresponds vaguely to a covariance matrix that hasn't been normalized. I mean, obviously a covariance matrix has values between 0 and 1, but a gram matrix is what it's called, doesn't have that type of nice normalization. That's what is considered as style space. Okay, so these are some of those initial results from that algorithm, and I'll get into kind of how we can improve that in just a bit. You can see, for example, here, Brad Pitt's beautiful face has been marred by the algorithm. It's like added a slash here. His eyes, he looks a little bit like Sylvester Stallone, kind of. So not the most flattering results. And as you can imagine, our users who love posting selfies of themselves, not so happy with those Sylvester Stallone eyes. So enter CuDNN, or also known in the literature as neural patches. And so this is work that's been done by one of our colleagues. So one of our employees at Lambda Labs, a guy named Chuan Li. So Chuan Li, and so this is essentially doing exactly what one of our viewers today have brought up, and essentially it goes like this: you generate the far right image that you can see here by using patches of the center image, okay? By basically copying and pasting patches of the center image, by finding correspondences deep into a network. So you'll go on to, like, let's say, the fourth layer of a VGG, which is essentially at that point class labels, like we've seen going all the way back to these visualizations, right? I mean, you look at layer 4 or something, layer 5, these are essentially classes. So you come up with class correspondences by looking deep into the network. So instead of looking for correspondences in pixel space, which would be like the kind of the old way of doing it with, let's say, SIFT, and you're coming with like SIFT feature correspondences, right? No, we're gonna do that correspondence kind of in a space, using manifold learning terminology that is kind of a little bit less entangled, right? And so you're gonna be able to come up with much cleaner correspondences in, let's say, ReLU 4.2 of VGG, for example. And then you basically use the patches from the center image to do that. And so that's exactly what you suggested. And as you can see, these results are much better. I mean, for example, he doesn't have the Sylvester Stallone eyes. This is actually the same style image, by the way, as this one.
By the
So,
way, if you point to your computer.
oh, sorry, I'm sorry, yeah, sorry. This is actually the same style image as this, right? And so you can see here, he actually has the nice Picasso eyes and everything. Okay, so that's what's kind of colloquially known as neural patches. All right, question?
Was that an extra mouth off to the left on the right side?
Yeah, look, that does look a lot like that. And you can see that's because the network kind of, if you look at this little patch here, it kind of does look a lot like a mouth. You see that? Essentially, there's the dark line with the light line underneath it. And so that's a...
You're looking for a bag of there's a bag of features, and you can take the middle one and just springboard up into...
Yeah, but the really important thing is that all of these features are matched in a way that, is completely learned. So, in the past, you'd have some sort of hand-tuned features. These are all 100% learned features of the network. And I think that it's really important to actually go back to this image right here and really show it's quite, this is probably, I'd say, the real fundamental result of deep learning is that the network ends up learning these hierarchies of basically edge detectors, which gets composed into kind of shape detectors, which gets composed into more advanced classes. And the allocation, or we would say the disentanglement of these different features happens kind of automatically during the training, during the labeled supervised training. And then that's a really important result to be learned here, which is, no one uses hand-tuned features anymore, but the point is that I think that's a key result here.
So for the input layer, you give both the images. For the input layer, you give both the images, style image and the content image. For the input.
For the input. Yeah, I'm gonna. So the question is, for the input image, do you use both the content and the style? And the answer is yes. I mean, you're basically taking the content and style, running them through the network, and you're gonna get to like a deeper layer, and then you're gonna come up with correspondences between. So for example, those two eyes, like the eyes in the Picasso painting and the eyes in the photograph, are gonna be very similar to each other in content space. And so it's gonna use that, say, okay, well then we should use the patches from the region in the painting to repaint the content image using those features. This is another good example of that. And this is a good comparison between I'll say the naive Gatte's approach and the Tron Lee, our employee Tron Lee's approach. And you can see that in one of them, the wheels are kind of all screwed up and there's not like clean lines. Just to go back to what the content image here is, the content image is a SUV and essentially a sports car or something, right? And then like the style is like a VW Bug. So it's been able to recreate a sports car and an SUV in the style of a VW Bug. It's a very creative thing. I would say that if you were to talk to an industrial engineer, they'd be like, oh wow, that's a good job. Okay, there's a question over here.
So you said you were using really supervised learning here. How can you really do supervised learning because you don't really know what the answer is supposed to be? So is it some sort of a combination of supervised and reinforcement learning?
Okay, so the question was, okay, there's a statement of you're doing supervised learning here, but is it really supervised learning? This is not supervised learning. The network was trained with supervised learning. I should clarify here. The network that is, we'll just say, for example, going back to this, the content loss function here is with a VGG, let's say a VGG network that's been trained in a supervised manner with, let's say, ImageNet. But its weights are frozen. It's pre-trained and its weights are frozen, okay? And we're using that to basically, as a function, to create a content space, and we're using its gram matrix as a function for creating a style space, which we can do this joint minimization in.
Even if VGGNet was not changed specifically for faces, but for like 10,000 categories, if I know.
So the question is,
So it works very well.
yeah, so the question is, the network has been trained, well, the question, anyways, the point is the network has been trained for ILS VRC, right? ImageNet, essentially.
It's 10,000 categories, not just faces. One face category.
Is it 10,000 or 2,000? Anyone? 1,000. It's 1,000, right? Yeah. So it's 1,000 categories, right? So it's not 10,000. But yeah, so it's basically been trained on 1,000 categories. It's ILS VRC. That's the data set. But the weights are frozen. Okay, so. Essentially, we're using neural network as a representation, as a representation for. Okay, so the question.
Yeah. So the benefit of finding the correspondences is that you can use eye styles for the eye content and mouth styles for the mouth content.
Yeah, the question is.
Well, the question is really how do you treat the style and the content really fundamentally differently? What do you draw out of the eye styles to affect an eye versus a mouth style to affect a mouth?
Yeah, so the question is, what do you draw out of the eye styles to affect an eye, or what do you draw out of the mouth? I guess maybe to rephrase your question is like, how do you come up with these correspondences in the first place?
How do you treat the content and the style differently, really fundamentally?
Okay, yeah. So in the CNN MRF paper, what they do is basically the photograph and the painting are both run through a content network. Okay, correspondences are found between the photograph and the painting, and then you use patches from the painting to recreate the patches in the matched region, I should say. Patches in the matched region of the painting to recreate the photograph as that painting.
Is it just a matter of merging those
You end up using a gradient descent process, but the point is that you're descending with that particular region, and you can see that this kind of results in better results than just that, I will say, naive neural style approach, which kind of ignores all content. Okay, so well, these all take kind of minutes, order of magnitude to do. So you obviously want to rephrase these as some sort of feed-forward network, which can be more like order of magnitude tens or hundreds of milliseconds. And so the way that you go about doing it essentially is you will retrain a forward pass network. So in the same way that here we froze the weights of VGG and are doing gradient descent and updating the data layer, what you do when you're training a feed-forward network is that we're going to hold the style image constant, and we're going to show it a bunch of content images, and we're going to have the feed-forward network kind of replicate the feature activations of both the VGGs. Of VGG, so you have a kind of a smaller network that's the feed-forward network. You have VGG here, and you're trying to have that small network kind of replicate the feature activations of VGG in the feed-forward pass. And so, and when it's interesting because when you're actually backpropagating to update this result image here, you're updating the data layer. This is like kind of uncommon if you're doing some sort of training for classification, right? You usually don't update your data layer, you update the weights when you're doing your backpropagation. But here we backpropagate all the way to the data layer and update the result. Essentially what you're doing when you're doing the feed-forward network is that you say, hey, well, let's actually do those weight updates. But we're going to do it on a smaller network that's designed to be feed-forward. And so we're actually use those gradients to update weights. But and so instead of updating the data layer, you're actually updating the weights of a feed-forward network. And I can give you a demonstration of that right now. So first, I can show you this app that we've made called Paintbrush. And you can also use this if you download Microsoft Sprinkles. I don't know if you've seen this, but we also have they call our API for Sprinkles, and so you can. So we'll all take a selfie here. Okay, everyone smile and look good. Sorry if I don't get you, but it's okay. And so you can see that we can do this relatively quickly. It's not 3 minutes at least. And maybe the more impressive thing, and this is kind of related to some of my previous work at Perceptio, is that we can put this into airplane mode. And you can see it's orange, so it's airplane mode. And it'll still work. And just to prove that there's no trickery here, so this takes about 500 or 600 milliseconds. And just to prove there's no trickery here, I can show you a real-time version of this. Okay, so boom, and we've got kind of a real-time neural style with a few different filters. I don't know if you guys can see this at all, but we do have something that's kind of semi-real time running locally on the phone. This is still in airplane mode. It's running on the phone's GPU. That's all. It's all possible. And so that's kind of what you want to accomplish with the feed-forward implementation.
Was the implementation based on like TensorFlow or something else?
The question is, what is the implementation based on for this particular thing? And the answer is, I have rewritten essentially the forward pass. So it's quite straightforward. You just rewrite all the forward pass logic for a variety of different layers, and you're able to basically you port a network down. There's a little bit of work in terms of quantizing weights and maybe reducing the size of your network architecture. But if you quantize down to 16 bits, you can keep most of the quality of the results of the network. And so I guess yeah. The answer is it's a custom thing. It's you basically are writing GPU shaders.
Are you using the Apple's metal performance?
This particular one uses metal. So we use the metal performance shader for convolutions, but there's a few different layers. For example, transpose convolutions, which is essentially the backwards pass of convolution. I guess it's the gradient calculation for convolutions, and then also the residual connections. So this network also has a residual layer. So there's a few that are just implemented in raw metal, but we also use the metal performance shaders just for the convolutions, essentially.
Are you doing any kind of video stabilization so that it doesn't flicker?
Currently, that's actually run on a frame-by-frame basis. It's not convolving over time or anything like that. All right, so you can see kind of going back to comparing this with the original kind of Gatte's paper. We've got Brad Pitt's face somewhere here. There we go. And then this is, I'm not as handsome as Brad Pitt, but I think the result looks better. You can see that basically the background has been applied to the background, the foreground has been applied to the foreground. And so this is kind of our own, it's unpublished work that we've done with Tron Lee, the guy who published that paper. You can read all of that. We'll get to a reference to the slide soon, and I'll talk about that. But this is kind of our own proprietary improved version of neural style, and you can see that it's not bad. It's much better than kind of. At least I don't have the Sylvester Stallone eyes. Okay, so the next part of this I think is important. Is we're talking. I will briefly go over Ganz, because I think this is a really important and exciting part of generative models in general. So all of these images are generated with the generative network on a GAN. And so you can see some faces here. These look relatively realistic. They look like kind of people that you might see on the street. And these look like album covers or something, right? And so essentially, this is from the DC GAN paper, which is by Radford, Metz, and Chintala, and who's at FAIR. Sumit, if you lurk torch GitHub, you'll see that he's like kind of the maintainer for that. And you'll all be happy to hear that just like Word2Vec, these GANs come up with very well-organized latent space representations that can do normal vector arithmetic with. So for example, we can start with a latent space vector for man with glasses. We can subtract out man without glasses. And we can add in women. So we have, I'll walk through every step. So man with glasses minus man is glasses, right? Everyone, glasses? Okay, glasses plus woman is women with glasses. Great, so we've got women with glasses. And this actually works, which is a great result, and is very promising that we can do a lot of the stuff. If you've read the Word2Vec paper, you'll be familiar with kind of like the king minus male plus female is queen type of logic. Very valuable. Okay, here's like kind of a base. I'm going to run over this very quickly because I'd like to open it up. We've kind of been doing Q&A intermediate, but here's my 1 minute and 30-second GAN description. Bear with me. All right. GAN, essentially, there's two phases to it. Phase 1, you sample 10 from n from real data, n from generated data. You pass it through a discriminative network. It tries to say, okay, well, what is the probability that x input for all of those n plus m x's was sampled from the data generating distribution, right? We're trying to model the data generating distribution so we can sample from it. All right. Then you backpropagate that loss. Essentially, you say, okay, you did wrong here, wrong here, wrong here, right here, right here. You backpropagate and update the discriminative network. Okay, next step is you will sample a noise prior. Essentially, you have a vector of, multivariate Gaussian. You have a few different Gaussian distributions. You'll sample from that noise prior. You'll pass it through a generative network. That will generate an image. All right. We then pass it to the discriminative network. The discriminative network says, okay, this is either real or fake. You backpropagate through and you update the parameters of the generative network. Okay, we have like 30 seconds left. Then that's it. You just kind of repeat this process in an iterative fashion. Let's update the discriminative network. Let's update the generative network. And essentially, G is trying to trick D. Generative network is trying to trick the discriminative network into passing off its data as real data, meaning data that's been sampled from the original data generating distribution. And the discriminative network is trying to say, okay, well, it's actually just trying to discriminate between real and fake data. Here, 0 meaning that it's generated and fake, 1 meaning that it's real data, so that's the red and the green. Trust me, the color logic actually does work out. All right, so that's 1 minute and 40 seconds. But that's what a GAN is at the very high level. And so then essentially what Radford, Metz, and Schintala did was, essentially generalize this to convolutional networks. And so that's kind of the results that you're seeing here. This paper was published in 2014 at, I believe, iClear. And it wasn't really maybe until a little bit later that it started really picking up being used. Wavenet is another example. We don't have time to go into it, but you can look it up online. Anyways, so a big part of the value of this talk, guys, is you kind of being walked through the history here. And please take a picture of this references slide. If you take a picture of anything else, it has the GitHub links, and it's got all the different things that you can just clone, futz around with. That's how you learn. And so just take a picture of this slide, and you can ignore everything else, and then you just go through everything. Yeah, I can put this. We'll do a blog post on the Lambda Labs blog, but still take a picture of this anyways, because that may not be for another couple of days. So, all right, everyone done? All right. We'll keep it up for a little bit. What was that question? Yeah, and so finishing up, some shameless promotion, as always. So Lambda Labs pays the bills by selling GPU workstations. And so if you work at a company that buys GPU workstations, or we also sell rack-mounted server appliances, you come up here. I've got these quotes for you. I gave you guys a really nice discount, same discount I gave to the folks at GGC 2017. And you just come up here, grab one of these quotes, send it to whoever buys things at your organization. You can call me up. You can talk shop. One of the advantages is that we kind of know what we're talking about, relatively speaking, in terms of deep learning compared to call up Dell EMC. Try and ask your Dell EMC or HPE rep what a GAN is, and we'll see what they do. And so you can come and work at Lambda Labs as well. So we've got a relatively small team. Includes Dr. Xuan Li, who you've kind of seen some of his research. That was with the Picasso, kind of the thing that you came up with on the spot. You should have published before him. And you come and work with us. We've got a nice team. We're just down the street, Bryant and Everett. It's downtown Palo Alto. Very nice little office. And that's it. Now we're going to open up for questions. Come up to me if you want. Here's a quote. You can get your $750 discount too. So now questions and answers. All right.
Okay, so maybe just raise your hand if you have a question. It's nice if I give you the mic so that you can talk into the mic and our viewers at home will hear not only the answer, but the question that originated it. Introduce yourself, please.
Sure, Steve Ganz. I have one more question. The equation you had up before, could you put that up again? Towards the end.
The loss, this one.
Yeah.
This one right here?
One back. Yeah.
This one?
No, the pictures. Yeah.
Oh, this one, okay.
Yeah, I imagine if you were to add the female first and then subtract the male without the glasses, it wouldn't work as well.
Yeah, that's right, because, yeah.
I'm curious. This is really intriguing, but I'm wondering what are the rules for this sort of algebra?
We're going to add the women first and subtract the man
without the glasses after.
We had a big conversation about this actually, about essentially whether or not. The question that you have essentially is this a vector space? That's the fundamental question, right? Are these operations commutative? That's a really good question. I don't have the answer. We were just arguing about this. It devolved into a huge argument. but I don't have the answer for you. So, if it was a vector space, then the answer is yes. If it's not a vector space, then the answer is no.
Seems like it's not, but
Unless you saturate your activation levels, then you lose anyways.
I don't know.
In terms of computing operations, I mean, in the embedding space, it is a vector space, right? It's Euclidean space.
Sorry, the question is what? Or the statement is?
In the embedded space, it is just a vector space, right? It's Euclidean space.
Well, no. I mean, so
n
that's the
dimensions.
point. I'm saying it's not clear that the embedding space is a vector space. Like, it's not clear that that you have like a field. Like, it's not clear that it's really not clear that the embedding space is a vector space.
So what are the operations? What's plus mean in this space then?
What are the operations?
So what does A plus B in the space mean if not a Euclidean?
A plus B in this space is typical vector operation.
Right.
I mean, we're doing a vector operation. It's not clear. I mean, so this kind of works, right? You still need to do some sort of like nearest neighbors. This kind of works. The point is that it's still not clear whether this is a real vector space.
Semantically, perhaps not, right? But
yeah, I mean, vector
mathematically,
space is a very well-defined thing. I mean, you have like a field and vector operations.
So it should work. The equation should.
Yeah, so this is suggestive that it might be, but whether or not that commutative property holds, and there's still questions about that.
Okay.
Whether or not this is a real vector space.
So you're in face space, so to speak. If you had a man with glasses, subtract a man without glasses, and then you put a dog in there.
Theoretically, right. So once again, this is talking about kind of like the organization here. Because there's vector spaces and there's mapping between the semantics.
This one is getting a little deep.
Yeah,
Why don't
yeah,
we? This is one of those things you later mob Stephen after the
Sure.
Q&A during the networking phase. Maybe if there are some other questions, we can return to this one in the more casual phase. Someone in the back. Hang on, I'll
If
jog.
we can solve right now, we can publish a paper together. Is my point.
Hi. So, quick question. I'm Gabe. Hello. I do
Gabe.
autonomous vehicle stuff. You mentioned that your app was doing sort of this work on a frame-by-frame basis right now. Can you speculate at all about how you might? Sorry, is louder better?
No, I can hear you. I can hear you. You can
Great.
specify a little bit how you might.
How you might use sort of time here? Can you specify how you
Yes.
might do this on a non-frame-by-frame basis?
Yeah. So the gentleman over here, Gary, in the same color jacket as my shirt, kind of brought up this point of, are you doing anything on kind of more of a temporal basis? Essentially, what you do there is you would convolve through time, right? You would have a bunch of frames. You'd have a convolutional filter that wasn't just a bunch of convolutional filters on a 2D spatial image. You'd work with a 3D volume, and you would convolve that over time or something. That's definitely considered. There's some research in adding like kind of temporal priors to this neural style process, but in terms of a feed-forward version of that includes temporal information, I don't believe there's anything. So if you want to publish a paper on that, then you might be able to get published in a good journal.
Next question. Yeah.
Are you aware of? Thanks.
But I would add one more thing to that, which is this. The feed-forward version of this is relatively stable. On a frame-by-frame basis, it's relatively stable. So you really might not get too much out of that, is the point. Unless you had some very good temporal stylistic data. Because remember, these are paintings and not some sort of like, Van Gogh wasn't doing, shader programming or like visual performance art, right? These are 2D paintings that these are being trained on. So if you had some really good performance art, maybe that would be something that you want to train on. But in terms of like from a photographic perspective, these are relatively stable frame-by-frame basis. Just wanted to answer that more properly.
Okay,
Next question.
Hey, my name is Atul. I've worked on some of these creative applications on using vision and music generation and stuff like that. So question for you. So have you used the Prisma app
Yes, I have.
Are you aware of, do you know what kind of network they use
Yes.
to train or to do their inferencing?
Yes. If you took a picture of the references slide, they're using they're using perceptual losses for real-time style transfer and super resolution. Johnson, Fei-Fei Li. There's one more guy. I'm so sorry for that guy. I wish I was it? No, it's not Karpathy. It's not Karpathy. It's Johnson, Lee, and then one more guy. I'm sorry, I'm forgetting your name. It's Johnson, Lee et al. 2016. That's the paper that they're using. You can clone that repository and make your own Prisma. Although I will say that the deployment aspect of that is significantly more difficult than the actual deep learning part of it.
Okay.
I'm saying that is, say, doing GPU deployment at scale.
Yeah. So do they do this, the inference, the image generation part on mobile, or do they actually run it on
I believe that they in fact do have some portion of their filters running on mobile. I know they have some portion running in the cloud, but the vast majority of their filters are running locally on the phone as well.
Okay. All right. Thanks.
Yeah.
And have you worked with any music applications?
So there's some very interesting. I personally have not. Most of my research and most of my work has been in the image space. I was going to show you the Wavenet example, which is a really good example of temporal generative network. They use LSTMs for that. They're actually generating the actual waveform, unlike prior research that kind of typically work with MIDI data, right? You know, if you know MIDI data, it's a very discrete, high-level representation of musical notation. And so they're actually generating waveforms, and I'm not. That's not really my personal area of expertise.
So, yeah, my name is Norberto, and one question I had is like when you talked about the style and the transformation, how you learn the style, you looked at it seems like local similarities between those features where you extract the style from. For example, in your example from the cars, it kept the distance between the tires the same and all that. But if you think about Picasso and art generation, is about abstracting the concept itself. So the nose and the eyes should still be understood as nose and eyes, but the relation between those should not be maintained.
Yes.
So how do you innovate on that space of changing the abstraction of the object, but changing it completely, the local order, but still maintaining the concept of a face?
Yeah, so I've still got my mic. So that's a really good question. We've talked a lot about this. How do you maintain kind of the, we'll call it the content stylistic features, right? Because it's really important to note, if you do the math, the Graham matrix completely throws out all spatial information. It's really important to note that. It throws out all spatial information. And so, the question, is a very interesting one. We've talked a lot about this. How do you kind of add creative content positioning? So, for example, you take your face in. This is maybe what would be considered an atypical Picasso, right? It's not like the eyes over here and stuff. And that's kind of an area of current research and future research. One of the things that we've talked about is basically having joint stylistic mapping to the result image alongside some form of like content, using the content of the style image a lot more to use for like some sort of layout. Theoretically speaking, you and I kind of recognize Picasso's work as being jumbled up features, right? Eyes and mouths not necessarily in the right position. And if you get deep enough into a network that really could understand that as a thing, then so I think that maybe some work regarding training networks to better classify between styles of artwork might be a good way of doing that. But this is really still like what would be considered state-of-the-art research. Attention mechanisms might be a good way of doing it, but that's definitely, once again, state-of-the-art research. I don't have answers.
Okay, we'll take one more question before we move to our networking break.
Yes, Steve Ganz again. So this is about creative uses of deep learning, and you started early on with deep dreaming. I think you said was pushing relatively dog images towards dogs and that sort of thing. That seems actually very much how pretty relatively standard human perception actually works. Have there been applications of this more towards machine perception as well?
That's a good question. Not to my knowledge. I don't believe that and someone if in the audience can correct me if they have some information otherwise. I don't believe that there's been a direct application to, for example, getting a better score on ImageNet or getting a better score on LFW or MNIST. I haven't seen that, and once again, correct me if I'm wrong here, but I don't believe so yet. I think so far it's been really just more focused on this kind of image generation space. Although that's an interesting hypothesis, I think that we'd have to figure out what is the actual thing that's going on in the human process, which is hard to understand.
All right, everybody. We have a little bit more time after the talk for a networking hangout. Meet your neighbors. Come up and mob Steven. Mobbing the speaker is a time-honored tradition after any of our talks. But it's also an opportunity to get to know the people who are here with you. Let's thank Steven now, and then grab a drink. And
thank you. Thank you, guys.
Thank you, Steven.
And if I'm talking with someone, you just tap me on the shoulder, and that will signal that I will just hand you one of these things. I won't necessarily break the conversation, and that way I can kind of do distributed or at least concurrent work here. Hi, how you doing? Yes, you can.
Do you have a